Good evening, everyone. So, uh, today, welcome to the class 9 of Deterministic Electrical Calculus. So, today will be a short class. So, last class we saw clean star operator and some properties of the clean star operator. We saw the least solution of the Fn equation, which was A star B, which is A clean star the clean star operator of A into B. Then we saw what a separative function was. We saw the separative closure operator defined on the complete diode of min plus uh, functions, and the complete diode was the set of min plus functions, the pointwise minimum operator and the convolution operator. Uh, we saw some examples of the clean star operator, then some properties of separative functions. Using these properties of separative functions and the clean star operator, we saw some theorems on separative closure operators. So today we'll see one more theorem of clean star operator, and then we'll go to deconvolution. So today's theorem is the first theorem is, so if f and g belongs to set of min plus functions, then f pointwise minimum g, the clean star operator of those both, is f clean star operator convolution g clean star operator. Right? So yeah, so we'll see. We'll first write the definition of use the definition of clean star operator or the separative closure operator. This is the sum I equal to 1 to n. F mean pointwise mean g ui such that I equal to 1 to n, y equal to t. This is t, right? Now this we can write as inf 0 less than equal to m less than equal to n. Inf summation I equal to 1 to n fui plus summation I equal to n plus 1 to n gui summation I equal to 1 to n ui equal to t. This is same as writing it as in 0 less than equal to s less than equal to t and splitting the inside in n summation I equal to 1 to n fui such that summation I equal to 1 to n ui equal to s plus inf n summation I equal to 1 to n gui condition on summation I equal to 1 to n ui equal to s ui equal to t minus s. This is basically infimum of 0 less than equal to s less than equal to t. This whole thing is f star and this whole thing is g star. So we see f star s plus g star t minus s is equal to f star convolution with g star at t. Okay, so we have proved this. So from this we can get a corollary. Corollary is also known as the efficient subadditive closure. So in this closure, what you do is you basically just replace G with E, right? And the theorem you get is let F belongs to F, be a function apply the same above theorem with G equal to F, you get F is equal to F star convolution E star, which is equal to F star convolution E, which is F star. So next we'll define the deconvolution operator. But before we go into the deconvolution operator, so we'll see. So this is actually the last operator that we frequently use in network calculus. This can be seen as the inverse operator of convolution operator. But the structure of nimplus diode, that is not a field, right? The structure of nimplus diode is not a field. And so only pseudo inverse can be defined on the nimplus diode. So first we'll try to define pseudo inverse, or what they call as residuation in complete diode. So we'll first we'll first look at the most basic concept of residuation before specializing them to the nimplus diode. Similarly, what we did to all the other operators, like first we'll define the residuation operator on uh, a diode, a normal diode, and then we'll specify it to specialize it to the nimplus diode. So before going to deconvolution, we'll define the residuation thing. So just to give a background, in algebraic structures such as fields, what you have is all elements have an inverse, right? Such that A to be equal to 1, and then you define um, the division such that A divided by B is equal to A into B inverse, right? So this is the inverse element. This is not possible in a diode. So, however, in complete diodes, what we can do is we can find the greatest solution of an inequality that can be defined, right? So what we are interested in a diode is we want to find X multiplied by A, diode order is B. We want to find the solution. So we want to find what X is, such that uh, X into A is less than or equal to B, right? So we already know that the diode order relation to be, so if A is less than or equal to B, diode order relation, this implies A plus B equal to B. So we want to find the greatest solution for this inequality, right? So for that, first we'll consider a complete diode B plus, this is a complete diode. So we'll define a right hand operator. So this is a right hand operator such that it takes x, gives x into a. So as the diode is complete, we know that from the property of complete diode, the product distributes over infinite sums to the right. So for any subset B, subset of D, we have RA, x belongs to B, x, right, is equal to, oh sorry, since I've defined this as a function, right? So this is plus x belongs to B, RAX, right? And if x is order less than y in diode order, then RAX less than or equal to RA. So any mapping, so now since this is a mapping or a function, any function that satisfies this property, we'll call it as lower semi-continuous property. Since x less than or equal to y implies that function. So basically x less than or equal to y implies f of x is less than or equal to f of y. So that is a lower semi-continuous. So now we define something known as RA hash, right? So RA hash is another mapping. So what that is give is if you take y, take sum of all x's in D such that RAX less than or equal to y. This mapping also is well defined because the diode that we are using is complete, and since it is complete, infinite sum over infinite summation is possible for all the elements of the diode. So what we say is RA, the function that we define, is the residuated mapping. RA hash is the residual mapping. So the RA and RS hash, they satisfy some properties. So those properties are RA over RA hash X is less than or equal to X, and RA hash over RA X is less than or equal, is greater than or equal to X. These are all diode order, right? So to show this, we can see that. So you have RA over RA hash X. This is equal to RA plus set of y's belongs to D such that RAY less than or equal to X. So this is over set of y belongs to D such that RAY less than or equal to X. RAY. Since all the RAYs are less than or equal to X, for the less than X, right? Similarly, RA hash RAX is sum of y belongs to D such that RAY less than or equal to RAX. Now the X becomes RAX, right? This is why this is greater than X. So RA hash is called the right quotient and leads to the residuation operator. So we'll define RA hash because it will be difficult to write RA hash every time. So we'll define the residuation operator by the symbol, which is RA hash over B. So how is this defined? Sum of over all sets X such that X cross A is less than or equal to the diode order B, right? So when I say X multiplied by A less than or equal to B, what do I imply by that is X less than or equal to B A. So similarly, so now we have done this for the right product and right operator. Similarly, we can define this for the left product, and similarly a left quotient can be defined in the same way. So when a diode is commutative, so the notions of the right product and the right quotient, they coincide with left product and left quotient. Okay. So next we'll define the min plus deconvolution as a residuation operator. So now we'll specialize it to the min plus convolution. So the complete diode that we'll be using is the set of min plus functions, pointwise minimum, and the convolution operator. We'll be using this complete diode, and we'll denote this as the deconvolution. So basically we have H convolution G greater than F. This implies infimum 0 less than equal to S less than or equal to T, HS plus GT minus S greater than or equal to FT. Right. So what does this mean? This means that for all T comma S belongs to R plus, such that S is less than or equal to T, HS plus GT minus S is greater than or equal to FT. Because the smallest S of this set is greater than thing. So every S is greater. If there was a S which was not greater than FT, then that would be the minimum and the first equation won't satisfy. So infimum is greater than something implies all the points in the set are greater than that point. So for all T, the inequality holds. And then for all Q comma S belongs to R plus, we have HS plus GU greater than or equal to F of S plus U. So now we are taking U as T plus T as S plus U. So we are making change of arguments which doesn't affect the inequality. From here we'll have all S belongs to R plus, right? HS is greater than or equal to, we'll have F S plus U minus GU. Since this is true for all S, we should true for the supremum u greater than 0, fs plus u minus gu. Right now, this equation, this operation, we call it as the residuation operation, residuation operator for the set of min plus functions, pointwise minimum, and the convolution operator. Right? This is what you'll start defining as the deconvolution operator. So since the inverse function is not available, so what we did was we took f star g less than or equal to h, and then we found what f is greater than or equal to g convolution h. Right. This is what we found as the inverse operator. So this is the convolution operator. This is the deconvolution operator. So we'll define the deconvolution property. So f comma g belongs to min plus set of min plus functions. Let f be g2 functions. Then deconvolution of f by g, which will represent it as f g. This also belongs to set of min plus functions. This is defined as f g supremum u greater than or equal to 0, f of t plus u minus g of u. Right. So basically f star g is the least solution of the inequality h convolution g greater than or equal to. Okay, we'll see some properties of deconvolution. So let f comma g comma h belong to the set of min plus functions. This you probably know what the complete diode is, pointwise minimum convolution. So for today, I'll just write down the 9 properties. I'll give a bit of insight from the properties. We'll discuss about the properties in the next class. So the first property is h convolution g is greater than f. This implies h greater than or equal to f deconvolution g. This is what we showed in the first thing. This is the basic inverse relation of the min plus deconvolution and the convolution. Right. So the proof for the first one is not that important because it is just the rewriting of the definition of the resolution operator. Okay. Second is f deconvolution g equal to min of h belongs to f, so that h convolution g greater than or equal to f. This is also one more definition of f deconvolution g, but this also is basically the rewriting of the definition of deconvolution. You don't need much insights to show this, so we'll not be showing this. The third one is the total operator convolution g gives you the total operator. right? And since t is the smallest element of f, the mean plus functions, so if you deconvolve it with any function, you get the smallest operator back, which is the t operator, right? We'll see the proof in the next class. Or if f is greater than or equal to g, this is not a diode relation, this is a normal relation. This implies f deconvolution f greater than g. So what does this show us? This shows that deconvolution is isotonic, holds the inequality functions. Similarly, uh, is isotone for right right hand functions and is not isotone for left hand functions, right? So if f is greater than or equal to g, this implies h deconvolution f is less than or equal to h deconvolution g. So it holds the deconvolution operator. If you do a left side operator, then the inequality holds. If you do a right hand operation of deconvolution for functions, then the inequality flips. So next is pointwise minimum. F pointwise minimum G deconvolution H is less than or equal to F deconvolution H G deconvolution. So this doesn't, the deconvolution operation doesn't hold doesn't distribute over mean place in pointwise minimum function, but it holds, it has an inequality, one side inequality. The proof we'll see in the next class. Similarly, F deconvolution G convolution H equal to F F deconvolution H deconvolution G, and similarly F deconvolution G deconvolution H. F deconvolution H deconvolution G equal to F deconvolution G deconvolution H. So something similar to an associative property. The ninth one is F convolution G deconvolution H is less than or equal to F convolution G deconvolution H, right? So these are the main properties of deconvolution, out of which the first two are just basically the by rewriting the definition of the reciprocation operator or the deconvolution, you can come up with the remaining proofs for the remaining properties. We'll see in the next class. And also we'll see some properties regarding deconvolution and maximum operators. And then we will have a short class on uh, what is the link between min plus and max plus. So there's something, so we have seen min plus diodes. There is something known as the max plus diode, right? So yeah, we'll see how the max plus diode is also defined, and that will be the end of next chapter. So by the next class, the this chapter will be done. Then we'll see subclass of functions. So in the next class, what we'll see is uh, we'll see some basic functions which are frequently encountered while modeling the uh, arrival and service process, such as leaky buckets or rate latency functions. We'll see how min plus operations can, by using min plus operations on these functions, we can compute efficiently the bounds or some parts, some performance notations that we want to calculate on those. Then we'll also see functions which are not as such as decay bucket or rate latency, but which have some properties of continuity and monotonity, which the flow arrival flows or the no, service follows. We'll see that could we come up with some interesting properties for those. Then we'll focus on concave and convex functions uh, on these classes. So we'll basically focusing. So in this chapter, we've defined all the four different types of operators. Next, we'll see how different functions react to these operators, right? So what happens if we take some type of functions and perform these operators on those functions to get some interesting results, right? Mm, yeah, so that will take maybe another 2 weeks. Um, Next, we will see are there some effective ways or efficient computational methods to calculate the min plus operators on those mm, functions which are difficult to calculate using the properties that we have defined previously, right? And what are those algorithms and such and such. So that will take another 2 weeks. So these these 4 weeks we will complete the course for the syllabus. So yeah, yeah, will see. Thank you for attending. I'll stop the recording.